A very warm evening, very distinguished members of SP Abuja section. You're welcome to our monthly technical meeting. This meeting is themed Beyond Sequestration, Harnessing CO₂ Mineralization for Environmental and Engineering Solutions. You're most welcome to today's technical meeting for the month of August 2025. And for the next 2 minutes, we'll be advising you to share the link to all of your colleagues and friends in the industry so that we can learn so much. We are so pleased to have a postdoctoral research fellow from King Fahd University of Petroleum and Minerals, Dr. Isa Mohammed, who will be taking us on this journey today. So please kindly endeavor that for the next 2 minutes, you share the links on your private WhatsApp groups, on your LinkedIn pages, so that we can have as many participants as possible who would learn from Dr. Isa Mohammed. Thank you so much, and I'll be back in 2 minutes to continue the event. Okay, my time is 5 minutes past 5 o'clock. Ladies and gentlemen, once again, you're welcome to this event organized by Society of Petroleum Engineers Abuja section. Can you do me a favor? Kindly go to the comment section and tell us where you're joining us from. Tell us which part of the world, which part of Nigeria you are joining us from. I would like to read. And of course, why you are so pleased to be in today's event. Kindly go to the chat box. Let's know where you are joining us from. My name is Ofofonono. I'll serve as your moderator for today. I'm joining from Abuja, Nigeria, and I'll be so pleased to know where you are joining us from. Of course, this is the August MTM. Every month, we share technical information regarding the exploration of oil and gas resources. And this month of August, we'll be speaking on harnessing CO₂ mineralization for environmental and engineering solutions. I will continue the events by making you understand our other events. The event is billed to last for 1 hour and 30 minutes. Of course, after the safety brief, we'll have the introduction of some of distinguished guests on the call. Then we'll have a welcome remarks by our section chair. After that, would have the biography of our speaker, and then the technical lecture continues, which will last for about 40 minutes. Then we have the question and answer, so you have the opportunity to ask and answer questions. Immediately after that, we'll have a closing remarks, and then we network. It's going to be very short and brief, and I believe you will give me all of your attention for the next 1 hour, 30 minutes. I see our section today joining from Abuja. Professor Ikechukwu Okafor. Thank you, sir. I also see Salihu Mahi joining from Nile University of Nigeria. And of course, I see a comment from Dr. Isa Mohammed joining from KSA. Yes, thank you so much for joining. You can drop your comments. So throughout the lecture today, we kindly appeal that you make use of the chat box. You can drop key takeaways so that other participants can also read and comment along. Also, the chat box will be used for the question and answers. Kindly take notes so that you can ask your questions, where Dr. Isa will respond to all of them. Switching gears immediately, we go to the safety brief, and I would like to kindly appeal that please, if you're not speaking, leave your microphone on mute so that you may not interfere with the deliberations we'll have today. If you want to speak, raise your hands using the chat button, and I'll give you the opportunity to A, your opinion. You can use the C for comments and the Q for questions. And of course, ensure you can still hear the fire alarm just in case you want to use your headset. Beware of the environment. And of course, we advise that you stay safe throughout the deliberations of today's event. We are so pleased to have amazing personalities join us today for these events. First on the call, we are pleased to have our leader, our champion of excellence, of course, the section chairman of SP Abuja section, Engineer Ikechukwu Okafor, PhD. A very warm afternoon to you, sir, or evening to you, sir, Engineer Ikechukwu. Confirm you can hear me, sir. Okay.
Yeah, and good evening, everyone. I can hear you.
Thank you. Thank you, sir, for joining us. And of course, your outstanding leadership in SP Abuja section. We commend your excellence, your drive for a culture of excellence. We're also pleased to have on the call the membership chairman for the section, Dr. Ogene Rume Ogulu. A very warm evening to you, sir.
Thanks. Good evening, everyone.
Evening,
thanks. Good evening.
Good evening.
Okay, we're also pleased to have the publicity chairman for SP Abuja on the call. Welcome you, Engineer Odafe Atebe. We have the SPE Cares assistant on the call, Justus Igwe. We also have several senior members on the call, and we say thank you for joining us today. Ladies and gentlemen, we switch gears immediately. Of course, let me continue by also saying a warm welcome, of course, to our guest lecturer for today, the postdoctoral research fellow from King Fahd University of Petroleum and Minerals, of course, Dr. Isa Mohammed. A very warm evening to you, sir.
Good evening, everyone, and thank you for having me today.
Evening, sir. Thank you, sir, for sparing your time to share technical knowledge to SP Abuja section. We are grateful and we can't wait to learn all you have upstairs. Ladies and gentlemen, we switch gears immediately to having the opening remarks. Of course, these remarks will be taken by the man who is championing excellence, championing a culture of excellence in SP Abuja section. He's also the Council Secretary for SP Nigeria Council, and of course, the outstanding section chairman of this section. Please help me welcome Professor Ikechukwu Okafor for his welcome address. Over to you, section chair, for your remarks, sir.
Thank you, Akwan. Please confirm you can hear me.
Yes.
Loud and clear.
It's not to be on video. I'm a little bit under the weather, but I have to be here just to try.
We hear you, sir. Sorry about that, sir.
Okay, that's fine. Okay, thank you. So the opening remarks for today's event is one that I hold close to my heart, and I want to say, distinguished ladies and gentlemen, team members of the Society of Petroleum Engineers, both within and outside Abuja, on behalf of the board of SP Abuja section, we warmly welcome you to this event. For the board year, our guiding motto or our briefs for the board year has been a culture of excellence, and it is very heartening to see that spirit reflected in the energy and commitment and professionalism that we have shown as members of SP Abuja section. Permit me to take a moment to celebrate and appreciate all our members who represented the section at the just concluded 1925 in Lagos. Indeed, your participation, your contribution, and your visibility continue to position SP Abuja as a vibrant and impactful section within SP Nigerian Council and beyond. Indeed, for the many who won award and for your contribution, you've made us proud. Today, we are privileged to hold an insightful lecture titled Beyond Sequestration, Harnessing CO₂ Mineralization for Environmental and Engineering Solutions, to be delivered by the enterprising Dr. Issa Mohammed, who is the postdoc fellow at the King Fahd University of Petroleum and Minerals. This topic could not be more timely as it speaks to the intersection of climate responsibility, engineering innovation, and its sustainability and the future of our industry. I want to encourage us to listen with open mind, engage with thoughtful questions, and take away fresh perspectives that indeed enrich our personal and professional journey. Once again, I thank you for being here, for your continued commitment to advancing the values and mission of SP International and SP Abuja section. Together, let's keep building on our culture of excellence. Thank you and welcome.
Thank you so much, Section Chair, for that very insightful welcome address. Ladies and gentlemen, let's get started. Of course, if you can see your screen, you would definitely be seeing the profile of our very distinguished speaker. Of course, our speaker, Dr. Issa Mohammed, is a postdoctoral research fellow at King Fahd University of Petroleum and Minerals, where he leads cutting-edge research in carbon capture and storage, with a particular focus on accelerating the kinetics and improving the long-term security of CO₂ mineralization. His work spans fundamental geochemical processes to field-scale deployment strategies, aiming to drive practical solutions for climate resilience. In parallel, he serves as a visiting consultant to Saudi Aramco, where he is actively involved in pioneering the application of CO₂ nanobubble technology for oil field remediation and enhanced environmental performance. His collaborative efforts with Aramco includes pilot-scale field trials and advanced evaluation of nanofluid behavior in subsurface systems. He earned a BA in chemical engineering from the Federal University of Technology, Vienna, an MSc in petroleum engineering from African University of Science and Technology, Abuja, of course, a PhD in petroleum engineering from KFUMP. Before transiting into the academia, he worked as a production engineer at Narak Energy Solutions Limited, Lagos, gaining valuable industry experience in upstream oil and gas operations. Bridging chemical and petroleum engineering, Dr. Mohammed's interdisciplinary research is helping to shape next generation solutions for CO₂ utilization, sandstorm control, and heavy metal remediation, contributing to global decarbonization and environmental sustainability goals. Ladies and gentlemen, to take us for the next 40 minutes, we kindly appeal that while he's speaking, you make use of the chat box and drop your questions so that he can treat them immediately after. Help me welcome, of course, the postdoctoral research fellow from King Fahd University of Petroleum and Minerals, Dr. Issa Mohammed. Over to you, sir. We'd like to hear your voice now, sir.
Thank you very much, and a very warm good evening to everyone, and thank you for having me, and also for providing us the opportunity to share a bit of what we're working on here at King Fahd University. May I kindly share my slide? Okay. Think just a minute. Think the slide should be visible, right? Can you see my slide?
Yes, please. We see it very well, sir.
Okay, thank you very much once again, and a very warm good evening to you all. Today is more like a discussion, right? Where I will practically be highlighting a few stuffs we've been working on for a couple of years, and some of the projects that are currently ongoing, and what we feel we should be doing really in terms of CO₂ mineralization, or an attempt to minimize the impact of CO₂ on our environment. So CO₂ itself and the discussions about CO₂ is really not news anymore. I mean, the global community is well aware of what the impact looks like, and even the critics at some point right now are beginning to agree to some extent that the impacts are real, and we need to take actions to mitigate this impact. To put into perspective what this problem looks like, at the moment, as of 2024 data, we are said to be emitting about 37 gigaton of CO₂. And it's projected that by the end of 2025, we probably will be around 40 gigaton of CO₂ emission. Now, there are different approaches to this. We could have this argument about whether we're going nature-based solutions or we're going engineering solutions. Now, it's also important to understand that while this whole debate about CO₂ is going on, let's get some things clear. This evening, I'm not going to be talking about the impact of geopolitics on the policies that have been made so far. I'm also not going to be talking about what equity looks like in CO₂ or energy transition missions. Because again, you want to ask the question, what is equity indeed? Do everyone have to contribute equally, or should we hold the major emitters more responsible and they should make more investments and more effort? This is not going to be the topic of discussion. We're basically going to talk about what we feel is real, what we feel is achievable, and what we feel is scalable. Now, as of today, in terms of the capturing capacity, the data shows that we have about 45 million tons per year in terms of the current state of the art facilities that we have. And it's estimated that before the end of 2030, or the developments or the constructions going on, if they were to be completed and they are operating at full capacity, we could maximize it to 100 million tons per year. Now, if you take a look at these numbers compared to what we're currently emitting, it's just a fraction of it. It's less than 1%. Now, it's also projected that in the future, we might have the capacity to increase the CCS project's capacity to almost 435. Even at that, it's still less than how many percent of what we are currently emitting, which tells us that there is more to be done compared to what we have at the state of the art. Most of the progress that we're making in these efforts, we have to achieve a scale that is really much bigger than what we have right now for us to be able to meet our net zero goals, if at all it is achievable. Now, CO₂ could also be used in different products. We could have it in urea production, we could have it in different products, right? But at the current moment, what we've been using or what we're producing from CO₂ account for less than 1% of what we are emitting, which tells you again the scale of the problem that we're trying to face. Now, if you account for direct air capture facilities that we have, about 53 facilities, now there are estimates that by 2030, if these facilities are operating at full capacity, we might be able to, will I say, capture or absorb just about 11 million tons. Now, put all of these together, it is still less than 5% of whatever we're emitting. Now, if we're supposed to be serious about this whole mission of capturing CO₂, mitigating its impact on the environment and all, we need to really go at a much more higher scale than we currently are. Now, geologic storage has been said to have the greatest potential. This is because of the capacity and the availability of different geologic medias across the globe. Now, if the capacity of geologic storage is put at maybe 8,000 to 5,000, 50,000 rather, gigaton of CO₂, it means that it has the capacity to absorb whatever we're producing. However, due to technical, will I say, drawbacks, scalability, and again, of course, the cost, this is still not yet achievable. We're still very much far behind reaching these or even getting close to these numbers. Now, if geologic storage is what we're looking at, there are different medias or approaches that we can use to store CO₂ in the geologic formations. Now, we have different mechanisms. We can classify them or can say them to be. We have what we call the stratigraphic or structural trapping. where CO₂ is immobilized in subsurface formations due to the presence of the cap rock. Now, there has been a lot of work in the internet or in the literature that actually concerns about this integrity of storage or the integrity of the cap rock, which is supposed to immobilize the CO₂. Now, for different research approaches, some people are using wettability, some people are looking at the geomechanical impact of CO₂ injection on the cap rock integrity. Now, due to the risk of leakages from the cap rock or reactivity of the injected CO₂ with the cap rock, a lot of concerns have been raised about the security of storage. Now, the second aspect has to do with solubilization. Solubilization means basically we inject CO₂ into saline aquifers or oil and gas fields, which basically the dissolution of CO₂ in brine. Now, CO₂ can dissolve in brine. However, this solubility approach has different drawbacks. And the drawbacks we're talking about here is that the solubility of CO₂ in brine depends on the salinity of the brine. So the higher the salinity, the less the amount of CO₂ we can dissolve. More so, it's dependent on the temperature and pressure conditions within the reservoir. Basically, the thermodynamic condition of the reservoir control the solubility. But the biggest drawback we have in terms of solubility trapping has to do with the time frame it takes to achieve complete solubilization. It's a very slow process, and simulations have put the time scale in thousands to millions of years. Now, we do not have that luxury to wait millions or thousands of years to, allow the CO₂ to solubilize. More so, there are risks of underground water contamination and many more. Now, the one which is said to be the safest long-term option is mineralization. Mineralization basically is the conversion of CO₂, which is a gas, into carbonate, which is a solid. So we could have magnesium carbonate, we could have calcium carbonate, we could have siderite, which is iron carbonate. So this is said to be more secure because, again, once it becomes solid, it's locked away permanently. However, mineralization in itself, based on field trials that have been reported, takes averagely, the earliest time we have is 6 months to 2 years to achieve completion. Now, we thought about it. Right now, we have PhD students, MSc students working on the solubility aspect of things, trying to increase the amount of CO₂ that could be solubilized, also trying to increase the security of the solubilized CO₂ to mitigate release. But we are more focused on mineralization because it's the long-term safest option. Now, but the problem of the time it takes to achieve complete mineralization, we believe it has to do with the kinetics of the process. When we mean kinetics, we're talking about how fast this thing could actually happen. So you ask yourself the question, if we're injecting CO₂ into the subsurface formation, a supercritical condition, and it goes into this formation and it's supposed to be reacting with the brine or the rock to become carbonates, you ask ourselves the question, what is going to be the cation source? Are we going to have magnesium carbonate? Where is the magnesium going to come from? Is it going to be from your rock, or is it going to be from the reservoir water, reservoir for the formation water? Now, if CO₂ dissolves in brine, it's formed mildly acidic condition, right? This brine becomes mildly acidic, and then we could have dissolution from the rock into the brine. That could be your cation source. But we believe that the kinetics is a rate limiting step, and this has to do with the ion release, either from the rock itself or the availability of ions itself in the formation brine. So if we actually, if we agree that there is enough cation in the brine, the second question is, how does the carbonate form? The cations have to react with carbonate ions to form calcium carbonate, magnesium carbonate, and the likes. And since we've said that this takes significant amount of time, the question is, what can we do to accelerate the kinetics of CO₂ mineralization? And that is where we come in. Now, our approach is quite simple. And what we've done here is, let's take some few steps back. Now, when we're talking about brines and ions, when the ions exist in brine in their hydrated states, which means that they are surrounded by water molecules. Now, for the carbonate ion to interact with this calcium ion, it has to overcome the barrier that is provided or that is present due to the water molecule in its hydrated form. So we thought about, what about if we dehydrate the cation? That could make it easier for the carbonate ion to interact with the calcium or magnesium or iron to form the calcium carbonate. That's the whole idea. But before we did that, we went ahead to see the different ions that we have in our brines. Let's say calcium, magnesium, sodium, iron, as well as some heavy metals because it relates to the discussion of today. How many water molecules do we have in their first hydration shell and second hydration shell? We decided that now that we know how many water molecules, for example, in case of calcium, calcium is surrounded by 6 water molecules in its first hydration shell. So what can we do to enhance the mineralization kinetics? Now, it is also important to note that when CO2 dissolves in brine, depending on the pH of the brine, we could have different components of CO2. CO2 could exist as a CO2 as a gas bubble. It could also become transformed to bicarbonate ion, or it could also become carbonate ion, right? The carbonate ions is what we require to form calcium carbonate, magnesium carbonate, and the likes. And you can see the pH range at which a carbonate ion exists. So we thought about deploying what we call a dehydrator. So we have a recipe. Once injected into the reservoir or once added to the brine, dehydrates the cation. And what really happened is the binding affinity of the calcium ion with the carbonate ion is slightly much higher than the binding affinity of the dehydrator and the calcium ion. So the carbonate ion is able to take away this calcium and form calcium carbonate. Now, the result was really astonishing. The reason is because we thought, okay, because we're talking about 2 years in field trials, if we could get it to be maybe 3 months or a month thereabouts, that would really be great. But we were able to achieve mineralization within 24 hours using the recipe that we've developed. Now, just to show you a bit about the results, and before we go into the application, let's go into the first section. And what have we done? I will explain what we've done at the lab scale and how it relates to what is going on in the field. So let's take, for example, you have a cell. You have a brine, which is rich in different cations. You add a recipe to it, which is our recipe, and then you expose it to CO2 at different pressures. You know the composition of the brine you've added. After 24 hours, you open up the cell, you depressurize the cell, open up the cell, and you will find precipitates, which is calcium carbonate, magnesium carbonate, as the case may be, depending on the brine you have added. That's basically what we've done. We've also decided to test the approach using seawater and formation water. These are compositions of Arabian Gulf seawater and formation water. Now, just to summarize what we're talking about this evening, we're looking at how we can use mineralization for heavy metal removal as well as sandstorm control, consolidating the soil. We're going to go more in details. Now, let's take a look at some of the results. So let's take, for example, we have a 7% calcium chloride solution. For example, if you add a recipe to it, at different pressures, at different temperatures, you're going to find this amount of precipitates. Now, the volume of calcium chloride solution we've used here, just for simplicity, I'm presenting the case of calcium chloride. The volume of solution we have used here is 50 ml. Now, for every 50 ml of solution, we are able to produce this amount of precipitates. So we collect the precipitates, we dry them, and we weigh them. Now, when you increase the amount of calcium chloride, weight percent, 20 weight percent, you're going to have more precipitates. Now, what was really interesting to us is when we realized that the recipe that we've developed could actually work even at atmospheric condition, which means that when you have a brine, and I give you this recipe, you add it to your brine, leave it in your office, your rooms, wherever you want to leave it at. So long it's exposed to atmospheric condition, it's going to absorb CO2 from the atmosphere, and you're going to have precipitation within 24 hours. We're going to go into the practical application of these as well. Now, when we tested the formation water, we also see the same thing, which means that the approach does work. Now, what we've done next is to characterize what we call the precipitates, right? So if we've tested an approach and we have precipitates which have been mineralized, we want to know what it is. So we run XRD analysis to know the morphology. I mean, the composition as well as the morphology in terms of SCM. Now, in the case of calcium chloride, 7 weight%. You see that majorly we have aragonite, calcite, vetrite. These are all calcium carbonates, and we have a bit of halite. When we take a look at the XRD result of the 20 weight% calcium chloride, we have the same thing. Now, at room condition, we also have calcite, and in the case of formation water, we have dolomite in some instance. And the reason is because formation water, like I showed you the composition, is also rich in magnesium. Now, when we take a look at SEM, the SEM result shows us the different morphology of calcite that is being formed as a mineralized product. So there are different forms of calcite, and we also have some halite, which is sodium chloride over here. Now, you'll be wondering, what is the practical implication of what we're talking about? Now, we have a recipe that when injected into the reservoir, along with your brine or seawater, it's going to convert the CO₂ into carbonate within 24 hours. Most of we're talking about is a recipe that could be used to purify air, which means that when you leave it to the atmosphere, it by itself absorbs CO₂ from the atmosphere, and we have mineralized product. Now, we're currently talking to company. We have a company who is a partner, and we're in the final stage of validations where we are looking at developing products that could be used for direct air capture. Now, this is against what the conventional direct air capture looks like, because the DAC systems we have right now have a major drawback, which is basically the energy requirement needed to regenerate the absorbent. Here we're talking about a low temperature atmospheric system that could absorb CO₂ from the atmosphere and applicable at surface and subsurface condition. That's what we're looking at here. But beyond all of these that we're talking about being able to achieve mineralization within 24 hours, you ask a critical question: how does it relate to the field? If I'm able to mineralize within 24 hours the CO₂ I am injecting into my field, what will happen to the permeability? What will happen to the injectivity? For sure, we're going to lose injectivity. No operator wants to lose injectivity within 24 hours when you've not achieved the amount of CO₂ injection you want. So right now we're working on a separate project, which is basically targeting the development of a switch mode-like system where we allow operators to inject as much as they want. And once they are ready, we can switch on the mineralization and have it blocked off in 24 hours. That is what we're currently working on in that concern. You also want to ask a question. In the field, we have sour environment. How does the presence of H2S affect the propensity of mineralization as well as the amount of mineralized product? We do not have the time to go into this. However, when question and answer takes us to this direction, we have results to show about this, because again, we want something that not just a lab result, but something that our very good neighbor and partner, which is Saudi Aramco, will take to the field and apply. So we've also investigated the effect of H2S on mineralization. And we can conclude to say the presence of sour environment does not affect the propensity of mineralization. However, it does impact how much of CO₂ can be mineralized. We'll leave it at that and we'll go straight into the application. And the first application we're talking about today has to do with heavy metal removal. Now, after seeing the result we had, being able to achieve mineralization within 24 hours, being able to do it, absorbing CO₂ from atmosphere, we thought, what could we do that solves a real challenge in real time? Because at the time, the Ministry of Environment had published a more stringent environmental requirement for wastewater discharge into the ocean. And Saudi Arabia is a desert country. It has a vast amount of desert. Most of the water that we use come from reverse osmosis, that's desalination through reverse osmosis. So from the reverse osmosis process, the reject water is produced, that's the waste from the reverse osmosis, which is amount of water that is heavily concentrated with these cations. At the moment, what they're currently doing is injecting it into deep wells, and they pay penalties for that. Now, we have waste treatment plants that treat their wastewater before discharge to the ocean, while in some part of the kingdom, these water are reused for agricultural irrigation. Now, at the time, reports were also shown that some fruits that were harvested from the the farms that used irrigated water from where treatment plants actually have traces of heavy metals in them. So we thought about how could we deploy CO₂ mineralization as a technology that is easily retrofitted into state-of-the-art facilities. We're looking at a technology that when we give the recipe to the treatment plants, most of the treatment plants have aeration chambers, right? So we're looking at a situation where we give you the recipe, you apply it to your aeration chamber, mineralization takes place, and we reduce the amount of heavy metal that is present in the wastewater, even before the treatment begins. So invariably, it's like a pre-treatment step before the treatment itself. And what we look at here, or target here, is a low-cost, economically viable option that could be easily fitted into what we currently have. So it's not a challenge or a bottleneck for treatment plants to adopt this technology. That was what we were looking at. Now, to demonstrate what we basically have done, I'll show you the results. So we took production or wastewater data from Bani Malik waste treatment plant in Jeddah, local groundwater, and then we took produced water data from Apkek and Shogam fields, which are units in Gawar fields, oil producing fields. And then Hindar as well. We took these three are basically oil producing fields in Saudi Arabia. So we took their produced water and then we reproduced them in the lab using different synthetic salts. Now, once we got this, what basically we've done here is we have this produced water and wastewater. We add our recipe to it, open it to the atmosphere, and monitor the amount of heavy metals that are present through ICP-MS analysis. That's basically what we've done. And to calculate the change, we minus what we have, what we had before, that's the initial value, from what we have as the final value, divided by what we have initially to calculate the percentage change. And this is the results we have. So the first case we have here, you can see these are the different heavy metals we evaluated. And this is at atmospheric condition, which means that when we have these fluids, this wastewater, we open it to the atmosphere, we add our recipe to it and allow it to absorb CO₂ from the atmosphere. And we monitor the change in the ion concentration for 96 hours. Basically, what you see here is that within 24 hours, in some cases, we have almost 100% removal of some selective metals. And in some cases, we have about 26% removal. Now, in the case of Saudi Aramco, they have a capturing facility, CO₂ capturing facility, and they pipe the captured CO₂ several kilometers to their injection site. So we thought about a situation where you have a nearby plant that allows you to capture CO₂, and we could bubble this CO₂ through your wastewater. Now, regardless of the approach you take, whether you allow it to absorb CO₂ from the atmosphere or you bubble the captured CO₂ through the solution, you have reduction in the amount of heavy metals. Now, what does this mean in all practical purpose? It does mean that in a treatment plant, which has an aeration chamber, you add this recipe to the chamber and wait 24 hours, and the effluent you will get from that chamber will be much less than what you started with. This will have implication in terms of efficiency, in terms of the workload that the plant needs to do before meeting the environmental standard that regulates the discharge. Now, the precipitate that we got from each of these cases, we decided to take them and we characterize them using XRF analysis to see or quantify the amount of metals. This is the precipitate. This is not the liquid anymore. And we can see the heavy metals present in the precipitates. But then you ask the question, we are saying or we are claiming that CO₂ mineralization could help to reduce heavy metal concentration in wastewater prior to even treatment. What is the mechanism through which these heavy metals are removed? Yes, we know the process is mineralization, but we still want to know how does this take place. To answer that question, let's take a look at the SEM analysis, the SEM images. We see from the XRD analysis of the precipitate as well as SCM evaluation, we see that the precipitates that have been formed in this case are majorly calcites, halides, and in some cases we have aragonites and even brucites. But how did the heavy metals get removed? From our understanding, what we come to the conclusion is that the heavy metals are removed by their infusion into the crystal structure of the precipitates that we have enforced. So when we enforce mineralization and we have this precipitation taking place, the heavy metals are found in the crystal lattice of these minerals. And this is how these are removed. And from a practical point of view, once you get the effluent out, you could get rid of these solids which are settled at the bottom of the pit. But now let's take it to a new dimension. We discussed these findings with our partner, Saudi Aramco, and the Saudi Water Corporation. And it was really interesting to see that this process, which is what we're currently working towards, is deploying this approach that we have found to be effective in removing heavy metals for critical mineral extraction from produced water. Now, if you take a look at the result I've shown you earlier, you realize that the removal rate of the different metals differ. Some metals were removed at 90-something%, some 20-something%, which means that the process is selective. So going forward, we have a project which is basically looking at the selective kinetic, will I say, alteration of the process to target specific minerals for extraction. This is critical because, again, we're going into renewable energy sources which require some critical rare earth metals to power these industries. So we're looking at deploying these for critical mineral extraction going forward. And that is the big picture we have in this approach. Now, next, let's go to the sandstorm problem. Now we're in the desert, and during the summer, it's usually quite hot. We could have the temperature as high as 49 to 50 degrees Celsius, and that is not something really comfortable to be in. But during the summer, when the wind blows over dry deserts, it moves or lifts loose particles from the topsoil or from the desert into the sky. And we have what we call sandstorm. Sandstorm. This could go as high as 150 meters into the sky. Heavy particle laden of sands moving across the zones. Now, these pictures you have on the slide were taken this year. This is in the Riyadh region, and this is in Qasim region. You can imagine the scale of this problem. Now, this does not just have environmental implications, it also have health implications, because again, when you have particles suspended in the air, you will have respiratory tract problems. Now, this does not just stop there. We could have these sands deposited on the road. We could have them deposited on key infrastructures like the mast, the telecommunication mast, on buildings, and you could have this sand pile up so much that it could actually even bury the road. We have a road we call dead end road. Basically, due to sand movement, the road which passes through the desert is completely sealed. Now, what you have here, this is Dammam. This is the eastern province of Saudi Arabia. Now, the samples for this experiment were taken along the Al-Hassa highway. Now, what the near experience that we have close to us here is when you're on your way to the airport or on your way to Al-Hassa, you're going to see piles of sands close to the road. And to remove this sand from the road, they use bulldozers to move them backwards. Now, sand movement is a serious concern across the globe. China also have this problem in the desert. Now, there are three major solutions that currently exist. The first is vegetation, basically planting trees to serve as windbreakers in these kind of systems. So when you have trees planted by the roadside, it serves as windbreakers, and then the sands are deposited beneath the trees. So we have arrays of trees planted by the road. The second type of solution is using fences. Fences is more like an engineered solution. So instead of planting trees, we take years before it fully grow. You can have fences developed with different porosity, such a material, such that they could serve as the windbreak and control the sand deposition to the locations you want. But these are reactive solutions and not proactive solutions. Now, the proactive solution approach has to do with consolidating the topsoil, which means that when you consolidate the topsoil, even when the wind were to blow, it will not have loose sand to pick up. Currently, polymers and binders are used. Some polymers are not biodegradable, so there are environmental concerns about their usage. Those that are environmentally friendly or biodegradable are quite expensive, and that has limited the field scale application of these technologies. So we thought about it. If we could deploy CO₂ mineralization to consolidate the topsoil, that could really work. It should be cheaper than the use of polymers. More so, it is less environmentally impacting. So what have we done? We developed a different recipe. Imagine you have this road with this sand, pile of sand. What basically we've done is we spray this sand with the recipe, which is majorly composed of brine, of course, allow it for 24 hours, and this recipe absorbs CO₂ directly from the atmosphere, reacts with the cations that are inside the brine, and forms calcium carbonate, which binds the sand grains together. There are two things you also need to look into. When we talk about consolidation of the topsoil, you also have to look at the strength that is required to break the topsoil. So we are concerned about the strength, we're concerned about the durability of the consolidated material. So to show you some examples of some laboratory samples that we have. So you have a sample that was a loose sand. We spray it with the recipe, allow it to absorb the CO₂ from the atmosphere, and you have it consolidated within 24 hours. These are carbonate precipitates, very visible from the top of the sample. But this is how it will look like. Now, you may be wondering, how deep can this go? Remember, when we're talking about sand dunes can go as high as 100 meters. That's how tall they could be. But we're talking about a solution that could consolidate the first few inches of the topsoil, so that even if the wind were to blow, we're not going to have erosion or sand movement. Now, we're also careful about the depth of penetration, and the reason is because we're trying to minimize alteration to the virgin desert. What is the Middle East without the desert? So we don't want to change nature or the natural state of things. We just want to have a protected layer that is just few inches on top of it, so that when the wind blows during the summer, we do not have sand being picked up. One important thing that we also took note of, and we were very particular about, is the permeability of the consolidated sample. So we did what we call microcity analysis. If you look at the top view to the bottom, you realize that the top is more consolidated. These harsh color stuffs you see here, we have the sand grains, which are the big bulks, and in between them, we have the precipitates, which are carbonates that we have formed due to mineralization. And as you go down the sample, you realize that the consolidation is not as much as the top, which is basically what we want. Also, you realize that there are some permeability left. Although in the Middle East, we have less of rainfall, but we want to make sure that when we do have rainfall, we do not have runoffs. So the water should be able to percolate through the consolidated sand tops. We also repeated what we call the medical CT to evaluate the samples that we consolidated, and we see clearly that only the top soils are consolidated, and below that we have what the original sand looks like. Now, to understand how these work, or to put it to perspective, this is what you have prior to treatment: loose sand, no cementing material in between them. Once you spray them with the recipe, it absorbs CO₂ from the atmosphere. Reaction takes place, mineralization occurs, and we have calcite in between the sand grains. So you have this sand grain, you have that sand grain, and in between you have carbonates. And this is what you have. Now, you could also take a look here. We have these material over here, which is basically the precipitates that we have, enforced, that binds the sandstone, or the sand grains. We could also have halite. We have aragonite over here. We have magnesium calcite over here. But let's take a look at a much clearer image. Now, this is what I'm talking about. You have sand grain over here. You have sand grains over here, sand grain over here. What is filling the pores is the carbonates, which has formed due to mineralization. But as good as this may sound as a story, the most important factor here for anyone to consider these as a solution is the economics. How cheap is it compared to planting a tree? How cheap is it compared to using fences? Because right now, Saudi Aramco has almost about 150 kilometers of fences installed along the Dammam Al-Hassa Highway, just solely to prevent or to control sand movement and sandstorm in those regions. Because again, the Gawar fields and the really prolific reservoirs are within that region. So we did the economics of our process. Now we chose major highways across the kingdom of Saudi Arabia. We have the Dammam Al-Hassa Highway, which is really critical to Saudi Aramco's operation. We chose Riyadh Dammam Highway. You can see the Mecca Jeddah Highway. Now, if you take a look at the Dammam Al-Hassa Highway, it's about 150 kilometers. The Riyadh Dammam Highway is about 380 kilometers. If you take a look at Riyadh Mecca Highway, it's about 870 kilometers. Now, what have we assumed when we did the economics? We assumed that this solution is going to be applied 50 meters to the left and to the right of the road, across the length of the road. Now, what is our thought? Our thought is that if we have this solution or the topsoil consolidated 50 meters on both ends of these roads that are sandstorm prone, it does mean that 50 meters away from the road, even if the wind were to blow, it's not going to have any sand to pick up, which will be deposited on the road. That's as simple as that. Now, it's also important to state that we are not saying this is the only solution, but vegetation, which takes time, fences, and consolidation has to be done in such a way that they complement each other. But if we compare our costs, okay, let's take a look at the amount of CO2 based on the XRD analysis, extensive XRD analysis that we've done of different carbonation processes that we've achieved at using different recipes. If we have a CO2 uptake rate of 0.86 gram per square meter applied to these highways for this particular solution we're talking about, the Dammam Al-Hassa Highway alone will be consuming about 12 tons of CO2 from the atmosphere. That's how impactful this is. Now, what are we talking about the cost? When we did the economics include the purchase of the materials required for the recipe, the transportation of the materials to the sites or to the roads, the application cost, because again, this solution can be either applied through sprinklers or you could have a truck go along the highway to spray this solution on the topsoil. When we account for all of these costs, at the end of the day, it costs less than $1 per square meter. Compared to fences and vegetation, which costs averagely about $10 to $20 per square meters to apply. More so, using vegetation takes years before the vegetation is fully grown. So we strongly believe that we are on a path to solve a key environmental problem with a solution that is so cheap that you could afford to apply it every month of the year. In closing, this is my last slide before I take too much of time. What we basically have achieved here is the deployment of CO2 mineralization for heavy metal removal from produced water, such that it reduces the cost of achieving environmental standard. And the reason we believe so is because the work done that will be required to meet the standard will be much less. Also, this could be deployed, which is something we're working on already, to mine critical minerals from produced water. In terms of sandstorm, we have a recipe that basically could cover the entire desert with carbonates. Invariably, what we are talking about is converting the desert into a CO2 sink. We spray the desert with a recipe, which is quite cheap, and it absorbs CO2 from the atmosphere. The reaction takes place and we cover the entire desert with carbonates. Also, these contribute to solving key health and environmental problems, which are really some key problems that the kingdom has made a focal point to address in a couple of years. Or currently, they're trying to solve these problems. Now, I cannot end this presentation without really thanking the university, King Fahd University, by extending the thanks to the president of the university, that's Dr. Mohammed Al-Skagaf, for his exemplary leadership. At KFEPM, we have a motto, and our motto is dream big and accomplish. He has always drummed this into our ears and challenged us to dare to dream big and follow its suit with the effort required to accomplish those dreams. Also, would like to thank the Dean of the College of Petroleum Engineering, Dr. Ali Al Yusuf, for providing the enabling environment to enable us to carry out research in a way that allows industry partners such as Aramco, SABIC, and many more companies around here to see our solutions worthy of application and adoption. I would also like to thank Professor Mohammed Mahmoud, as well as Dr. Dafal Al-Sheri, who happens to be my advisor and collaborators in this journey of basically seeing how we could, will I say, not just talk about improved kinetics for security of CO2, but to begin to think about how more we can use CO2 for to solving environmental problems. But the big picture and the goal of our research right now is basically trying to drive home the message of CO2 utilization. And the project we have with Aramco right now, which is headed by Professor Mohammed Mahmoud, is basically trying to put CO2 at the heart of every operation of Saudi Aramco. I cannot share more details other than that, but invariably what we're saying is for us to achieve the scale that we're looking and seeking, we need to begin to think beyond just sequestration and begin to look into how we can involve or apply CO2 in every application or every process that we have that permits the development of new technology that could solve real problems. Also like to thank the college for providing the state-of-the-art facilities which were used throughout this research. More importantly, I'd like to thank SP Abuja section for the opportunity to share our work. And with this, I'd like to thank you for the opportunity, and I call on you to join us in the quest to providing sustainable technologies that utilize CO2 and secure its storage in subsurface formations. Once again, thank you for the opportunity, and I'll take your questions if there are any.
Wow, that was phenomenal. That was excellent. That was brainstorming. That was intellectual. Thank you so much, Dr. Issa Mohammed, for putting so much energy to share CO2 utilization technologies to SPE Abuja section. Of course, we can see the comment sections. We can see everybody already applauding your excellence in presentation. So we're going to go straight to the question and answers. This is billed to last for only 15 minutes. So we'll pick a few questions. And after that, you may have to message Dr. Mohammed privately on LinkedIn so that you can probably send your other questions just in case time will not permit us to take all of the questions. Okay, the first question, okay, see some hands raised up. Okay, is there any hands raised up? Okay, there's no hands raised up right now. Okay, so we'll go straight to the chat box. Hassan Abdullahi, I imagine that the mineralization happened in the liquid phase. What is the efficiency of the mineralization process in the test you investigated? Specifically, what is the rate limiting step, the availability of dissolved CO2 on the availability of cations in the brine? And the second question is the CO2 availability in the limiting factor, how does the actual amount of precipitate formed compare with the thermodynamic maximum precipitation capacity? Okay, sir, you have two questions from him. You want to take it or
Yes.
take all together?
Yeah, I can just respond to Hassan.
Okay.
Dr. Hassan, actually.
Okay.
Hassan happened to be my cousin brother. So glad to have you here. So to address your question, the first question has to do with the efficiency of mineralization process. Now, when we talk about efficiency, efficiency could be, are you talking about the completion of the process? Are we talking about the exhaustion of the available cations? Now, let's go to the first question. What is the rate limiting step? Now, I put up this slide because we wanted to optimize the process, because mineralization can only be initiated at the pH condition beyond pH 8. The reason is because of the speciation of CO2. Carbonate ions only exist after pH 8, right? Now, but what really we have in the field is when you inject CO2, even if the pH of your brine or seawater was 8, once you inject CO2, what basically happens is that the pH drops to 5. So the thermodynamic condition required to initiate mineralization is already removed. And that could contribute to the long term, the amount of time it takes for mineralization to happen. Secondly, what you see on your slide, this is surface condition, which means at 30 degrees and at 50 degrees, which is possible in the Middle East. Subsurface condition, we're talking about 80 degrees and above, 50 degrees. And now, what this slide means is that if you have cation concentration, dividing cations, here, calcium, magnesium, iron, right? If you have dividing cations, 1 weight percent, 2 weight percent, 3 weight percent, depending on the brine you have, regardless of the amount of recipe you add, there are certain conditions that must be met aside the pH, which usually we think pH is the rate limiting step, the pH has to be achieved and all. But we figured that even if the pH were to be 14 and the amount of cation in the brine is not sufficient enough, mineralization will not be initiated. Right now I have a PhD student working on determining the actual minimum amount of divalent cation you require in your surface formation brine for mineralization to be initiated. That is the first case. So we believe the amount of cation is a primary rate limiting step, because again, in most fields, they expect the dissolution of the ions from the rock to provide the cation that is required for mineralization. CO2 is not a rate limiting step because that is in your control. You are the one injecting the CO2. However, the dissolution of CO2 in the brine also is dependent on the thermodynamic conditions in the reservoir. There are a lot of data available about CO2 dissolution in DI water, that's deionized water, sodium chloride, magnesium chloride, calcium chloride, but individual salts. Right now, I have an MSc student who is basically working on real brines and from the field to determine the solubility of CO2 in those brines, and if the conditions of mineralization will be met. So by the time he finishes his work, the goal is to ascertain how much of CO2 can be dissolved in field level brines. We're not talking about simplified brines like in most studies. We're talking about real brines from the field. Secondly, how much of cation is enough to initiate mineralization? And those will control the kinetics of mineralization. Now you're asking, if CO2 availability is a rate limiting factor, how does it actual amount of precipitate form captured with the dynamics? Okay. Now what we figured is there is a minimum value of cation required for mineralization to be achieved. Even if you have a solution that a brine that has, let's say 5 weight percent cations, right? If the mineralization process begins and the amount of cations left in the solution drops below that initial value we have identified, the mineralization will stop. So the key here is to continue to supply the brine with enough cation to continue the process. Now, a key question which has not been addressed in the literature, even by myself, which is something we're looking into, is there is a wrong assumption that the rock will keep giving you cations. That means the dissolution will continue infinitely. Almost all the softwares that are modeling CO2 process, dissolution, and all assume that the cation is continuously available. We find that not to be true. In fact, there is a particular pore volumes you have injected. Once you reach that pore volume, the rock stops giving cation. Rather, it starts absorbing cations from the brine. So there are a lot of factors at play here to answer your question, Hassan. So to pinpoint one and say this is it, no. Again, in real formations, there are all of these factors: the pH, the availability of cations, the kinetics of the dissolution, all are at play at the same time. And most often times, experimental laboratory experiments are too often simplified to represent reality. So this is the reason why we're taking the challenge to reuse real brines at supercritical conditions, because again, we have the facilities that can accommodate that. So I hope that answers your question. Can you provide a scale for the volume of CO2 that can be removed via precipitate? Now, CO2 in the atmosphere, it's a function of the recipe you start with. So if you're starting with a brine that has 3% divalent cations, you have less precipitate compared to that person who started with 48%. So the amount of cations matters. Again, the amount of CO2 in the atmosphere matters. But from all our studies, we've done this in different labs, we've done this outdoor, and we realize that the recipe or whatever that is going on, the geochemistry of the reaction really controls the amount of precipitate you can get, and not more about the uptake of CO2 from the atmosphere. But from all of our studies, our recipe can absorb CO2, and we look forward to more like a prototype design of products that could really achieve this at scale. And I don't know if there are more questions. What are some of the challenges encountered during CO2 mineralization? Okay, we're going to answer, I'm going to answer this question in two parts: laboratory-wise, experiment, and field scale-wise. Field scale-wise is basically availability of cations, geomechanics of the rock. I have an MSc student that is basically studying this right now to understand the impact of CO2 mineralization on the geomechanical properties of the reservoir rocks. So that is a problem, because you could as well induce fracture or microfracts, and these will probably, jeopardize the integrity of the reservoir. You're asking again, in the lab, there is really not much of a problem, but if we want to go laboratory, subsurface systems, we have to go at supercritical conditions. Now, it begs the question whether you have the facilities to handle CO2 pressure of 3,000 PSI or 4,000 PSI or 5,000 PSI. At our labs here, we have facilities that can handle that, both at static conditions and core flood systems. We have numerous core flood systems that can handle that. We could also have numerous core flood systems that can handle the acidity of the system. So the limitation basically has to do with the facility. Not really much of what you're doing, but the facilities to handle the conditions that you're trying to investigate. Do you inject the captured CO2 in the reservoir for enhanced oil recovery? Yes, I believe this is really something that's been long studied. There are a lot of literature about CO2 for enhanced oil recovery, but I have a problem with that. Not that it's not a good stuff. It's good to use CO2 or deploy CO2 for enhanced oil recovery, but most often times everyone is forgetting about a critical problem, which is asphaltene precipitation. Now, my PhD happened to be on asphaltene precipitation, and I'm amazed about how people talk about the use of CO2 for enhanced oil recovery, but nobody bothers about the impact of CO2 injection into the reservoir on asphaltene precipitation. I mean, CO2 is one of the gases that have been identified to precipitate, to induce asphaltene precipitation. And when asphaltene precipitates, we could have wettability alterations, we could have permeability impairment. Of course, it can be used for enhanced oil recovery, but you have to be careful to determine the condition at which it will not induce asphaltene precipitation. So is this technique for CO2 mineralization affected by high pressure, high temperature condition that are started with? Okay, we have tested this for high pressure, high temperature condition. It is not affected. In fact, the higher the temperature, the higher the faster the kinetics of mineralization. So it's good for us. H2S, in fact, here, this is it. I think this is the slide on H2S, right? So with H2S, this is what you have. Without H2S, this is what you have. Now, you also need to know that when you have H2S in your reservoir, H2S could also have its own speciation. So depending on the pH of the brine, you could have H2S as this or different, it could exist in different ionic states. And we have also investigated the impact of H2S on CO2 mineralization. I think that was published just like about a month or 2 months ago, thereabout. And what is even more important is we have also studied why some molecules do not work in sour environment. So again, I think you could take a look at that. We have the paper available online. You could have a look at that, and yeah. So H2S presence does not affect propensity of mineralization, but it does affect how much you can get to mineralize, right? So many times, okay, how do you capture the CO2 which comes out with produced water? Okay, so this is what we do. I'll give you a, am I even allowed to do this? Okay, I'll give you a schematic of what we're thinking about. When we inject CO2, let's say all of it is not mineralized, some of it is not solubilized, and we have it produced back, all right? You can have it separated at your top facility and resent back for injection, right? That can be, that is possible. But in our cases, we are actually not producing CO2 with the produced water. Instead, we are injecting CO2 with the produced water to extract or to mineralize cations in the produced water. Now, whatever effluent we have now is now reused for other applications like fracking operations. So basically, we have a program where produced water is treated by mineralization, and we have an effluent that supports water circularity and CO2 utilization at the same time. So basically, you can imagine how many million barrels of produced water we have per day. And Saudi Arabia is producing over 10 million barrels of crude oil per day. So a lot of produced water is, come to the surface, most of which is re-injected into the reservoir. And what we're looking at now is to take this produced water and get value out of it. You know, either we treat it through mineralization to extract valuable metals, or we condition it in a way that we can reuse it for other drilling operations or all of that. Yeah, so please, how do you capture? Okay, so I think, I don't know, but it seems like I've exhausted the questions that I have on the chat box.
Hello, Dr. Issa. Can I come in?
Yeah, sure, please.
Yeah, Akpan, please. Sorry. Good evening, everyone. Do I raise my hand up?
Okay, Ogolorume, yeah. Please go ahead.
My question is first is this. I was wondering. I wanted to see your economics for the operationalization of you guys' technology in terms of capturing CO2 along the highways. What did you put into consideration in terms of operationalization? That the CO2 being captured when it mineralizes, it's not going to be there, right? All throughout, you have to dispose it. You have to take it to your location. You empty your containers or storage tank. You open it up again and the likes. I wanted to ask for your economics in terms of the one you did, where you were able to say, okay, that CO2 mineralization for highways is far cheaper than that of planting trees. So I wanted to see your economics. That's your economic models. What did you put into consideration to arrive at such conclusion? Then two is that are there also opportunities for collaboration in terms of deployment of your technology, especially in Nigerian terrain, so that that is also a form of feed-based application that what you have, because I think during the SPNIEs, we had some guys from Australian University that came, they make presentations. Collaboration. So are there opportunities for collaboration, probably with researchers in Nigeria, to see how such technology can also be deployed in the Nigerian terrain, since most of your reservoirs there, they are majorly carbonate reservoirs, and here we have sandstone reservoirs, which also goes back to my third question in terms of deployment, whether you've considered this technology in terms of sandstone reservoirs as well. Thank you.
Okay, thank you, Dr. Rume, for your questions. I'll take the first one. I cannot discuss the details of the economic model, but what we factored into this. We did not factor in, okay, again, this technology being deployed for highway. Remember, the CO₂ is from the atmosphere, so that's free, all right? The bulk of the water that we're going to be using is from the Saudi Water Corporation or from the produced water from the fields. That is almost like a waste, so it will come at a very cheap cost. What we're paying for, really, the major costs, the economic model is more detailed that I'm sharing with you, but I do not have the permission to share all of the details. But what I can tell you is this: what are the big costs that we are incurring? The big cost has to do with the procurement of the materials required to prepare the recipe, all right? The transportation of this recipe to the field. Like I mentioned, this can be deployed either using sprinkler systems. So for the sprinkler system, it means that you will have like a substation which has like a big mixer or a pit where this recipe is going to be all mixed up, and the pump head is going to be, the suction is going to be within this pit, and it's going to pump through all the, what do you call it, the sprinkler systems, right? So that initial capital cost of building this facility is captured. Secondly, when we're talking about using trucks, you could actually hire trucks on daily basis or as per need to mix this recipe. So it's just like the same truck you use in mixing cement, right? You mix the recipes, you pump them into a truck, and then the truck move along the highway spraying it. So these are really the most expensive costs that we incur, because most, again, we should know that when we were talking about this technology, we're looking at something that converts waste to wealth. So the resources, the wastewater that is from the reverse osmosis water treatment process becomes our feed. Again, we deploy our heavy metal removal recipe technology first to clean the water to some extent, to remove the heavy metals before we use it for this approach. Because again, the environmentalists will not let you rest if you're going to inject heavy metals into the soil, all right? So in terms of model, I can't really give much of the details, but the values that we arrived at, again, we're talking about company level. We're not talking about university research. We're talking about a partner who is more like an investor in these already, that is taking these for pilot test. So we're currently doing the validation, the final validation test before we go for field trials on this technology, hopefully at the last quarter of the year. All right, that answers the first question, I hope. You asked about collaboration. We're very much open to collaboration. That's one of the reasons why, you know, this avenue or this platform really is important to us. And our university, like I said, also encourages us to collaborate with faculties across the globe. So very much available to collaborate, especially on how to domesticate this technology in terrains such as Nigeria. Now, in Nigeria, of course, you said we have sandstone reservoirs. Now, it may interest you to know that, I mean, as a Nigerian, while working in a carbonate-dominated system, we also have to think about home, right? So we came up with what we call in situ mineralization using ex situ cation source. So we have a section of the recipe or protocol that we've designed that is specifically for carbonate formations, because again, we are not expecting cations from carbonates. I mean, from sandstone reservoirs, sorry. So we have a recipe and a protocol that we've designed, not for carbonate, but strictly for sandstone. In fact, I have a student, an MSc student, I think Munir is the one working on this. His work is basically targeting sandstone reservoirs, mineralization in sandstone reservoirs, and evaluating the impact from geomechanical point of view of mineralization on the reservoir after mineralization. So, Dr. Rumi, I hope that answers your question.
Yeah, it's fine. Thanks for the explanation. Thanks. We'll talk more. Thank you.
All right. Thank you very much for the question. Oh, okay.
We have one last question from Lucas, and this will be the last question, ladies and gentlemen. Please, we have more questions. We kindly appeal that you follow Dr. Issa on LinkedIn. We have exhausted our time. So, Dr. Issa, you take the last question. In addition, please, Doctor, has your research been published so we can read? How do we get access to this presentation if your paper hasn't been published? Please give them your LinkedIn profile as well, or email address so they can all reach out to you for more inquiries, please.
Okay, for my LinkedIn, I think you can scan that. That's you can scan that up. Anyway, I'm very much on LinkedIn. And for the question about the papers, yes, the papers with these key findings have been published, so you can have a read at them. They're available on Google Scholar, or they're actually on my LinkedIn as well. You can find them on my LinkedIn page as well. So, and for the slide, okay, for the slide, I can share the slide, but I might have to do some engineering stuffs to it before sharing, if that's okay.
Fine, sir. Fine.
Yeah, sure. So because again, I have some slides that have multiple, images, or probably just opposed on each other. So I'll have to clean that up and make it, in sequential order so it doesn't, it looks clean, just like this slide, some of these things are disappearing and appearing again. So yeah, I can make the slide available. I'll share it with the section, and I think that can be made available. And everything I've discussed this evening, it's published. Yeah. So
thank you
once again for the
so much,
opportunity.
sir, for your time. Thank you so much for taking time to respond to all of the questions. Thank you so much for your wealth of knowledge. Ladies and gentlemen, we switch gears. You may stop sharing your slide now, sir.
Okay.
Let's wrap up the events, and we announce a few of other events we have in the section. Thank you. Please drop your comments and celebrate our amazing speaker, Dr. Issa Muhammad. Thank you so much, sir. So, ladies and gentlemen, if you have not joined SPE, if you're not a member of SPE, this is an opportunity for you to join. We have many benefits for both professional and student members. New membership fee at 6,500, renewal 69,500. However, if your renewal elapses where you don't renew on time, you will have to pay a restatement fee of 17,000 naira only. Please, if you want to renew, kindly screen grab the image you see on your screen and ensure you call Engineer Dr. Ogenrome Ogolo on the number, and he will assist you with renewal and payment details and all of that, just in case you don't have a dollar account. Yes, that's our account number on the screen. And of course, you can always go back to our social media platforms from YouTube. You'll find all of our past technical events. This one is live stream on YouTube. You can always go back and rewatch and refresh your minds. And of course, Facebook, Instagram, and of course, our email address. Send emails and we will respond to you as soon as possible. For our students and for those who would like to understand OPEC and the global oil outlook for 2025, we have a Real Talk and Real Topic series, which is coming up on the 4th of September. If you visit our social media page, definitely you'll be able to see the link where you can register and be part of this event. We have some stakeholders from OPEC, from the NUPRC, who will definitely give you a shed light on world outlook for 2025. Ladies and gentlemen, of course, we'd like to have the closing remark, and it will be taken by no other than, of course, our program's chair, Professor Kafayat Adeyemi, ably represented by the membership chair. The membership chair, please, would like to have you give the closing remark. Dr. Ogenrome Ogolo, over to you, sir.
Yeah, thanks so much, Dr. Issa, for the brilliant and wonderful presentation. You could see that most of the participants even stayed throughout the presentation, and because of the fact that you were able to give us details, data, and we saw a lot of science in your work. So thanks so much for sharing this knowledge with us, because our perception of CO₂ mineralization has been expanded through your presentation. So on behalf of the section chair currently here, even the program chair, I wish to thank you once again for coming to speak with us on this very, very technical matter. Initially, we were thinking that because our section is made up of more policymakers and few industry persons, but with your presentation, everybody is able to follow and see need that we not just only look at in terms of CO2 sequestration, but you have shown us another light in terms of CO2 mineralization, that even this technology can be deployed in our road, in our cars, to be able to curb CO2 emissions. So once again, on behalf of this section, we say a big thank you, Dr. Issa, for this brilliant and mind-blowing presentation. Thank you. And I wish everyone a good evening. Thank you.
Thank you. Thank you for having me.
Thank you for that closing remark, ladies and gentlemen. Thank you. At this juncture, please, we'd like to ask that you turn on your video cameras. Please turn on your video cameras. Let's see your face and let's take a quick screenshot for the gram. Please turn on your video cameras wherever you're joining us from. And then when I say SPE, you're going to respond with culture of excellence and you show us your thumbs up. Thank you, Usman Ismail, for turning on your video cameras. Thank you, thank you, thank you, thank you, Salihu Mahi, for turning your video camera. Akram Muhammad, yes, turning your video cameras. Please turn your video cameras. And when I say blessing to Kura, I celebrate you. Mutari Lawal, Bello Abubakar, thank you so much for turning your video cameras. Please, the rest of the call, just turn the video cameras. When I say SPE Abuja, you're going to respond with culture of excellence, and then you just show me your thumbs up. As simple as that. Let's wait for a few people to on the video cameras. Akram Mohammed, thank you. Odafi Atebe, we're waiting for you, sir. Section Chair, we're waiting for you, sir. Dong IL, we're waiting for you. Lucas Malami Mohammed, Assistant Program Chair, waiting for you. Okay, thank you so much for those that have turned your video. So, SP Abuja, respond with culture of excellence. You can unmute your mic now, please. Okay, Dr. Malami Mohammed, thank you. Thank you. Odafi Atebe, thank you so much, sir. Publicity Chair. Okay, SP Abuja.
Also of excellence.
I'm not hearing you. Are you hungry? I'm not hearing you. Okay, the last time so that we can make it amazing and then you can smile. I'd like to see your 32. Okay, are you ready? SPE Abuja.
Culture
Culture
of
of
excellence.
excellence.
Awesome, awesome. Thank you all so much, ladies and gentlemen. Until our very next event, do have an amazing evening. Bye for now.
Thank you.
Thank you.